Hi, Dylan. Hi, Dylan.
Hi, Professor Popovich. How are you?
Oh, peachy keen. How about yourself?
Pretty good.
Fine as kind. You and Jackson are here anyway. Ooh-wee. Ah, been a long day. Sorry I'm a little late.
You're good.
How'd you do on the test?
I could have done better.
Yeah, mine was all right.
Yours is okay?
Yeah, it was an
Did you
85, but that's, open to test. So
did you get this? Did you see the thing for the announcement for the extra credit?
I see that we have an extra credit assignment, but I don't know what it's for.
It's in the Dropbox. All you have to do is go to the Dropbox. There should be, if I'm not mistaken, I'm gonna stop share screen here. I believe, there it is. Okay. I believe if you go, are you seeing the screen now?
Yeah.
I believe if you go down to Dropbox, sorry, see extra credit at the bottom?
Yeah,
Okay.
but it's not.
It's not what?
It's not open.
It starts today at 7.
Okay, that was why.
All right. So basically, you're going to have 2 questions. One of them, yeah, guys, everybody that's out there, you have 2 questions for extra credit. Basically, I gave you a reaction, gave you 2 different amounts of the reactants. You have to tell me what's the limiting reagent, how much silver chloride precipitated, and sorry, just somebody else has to come in. How much silver chloride there was, how much silver chloride was there or was precipitated, and how much the excess reagent remains. And that's it for that one. And the second question is, guys, I don't know how, there was a lot of you used, this was the last problem in the test. A lot of you figured out that you could get the moles of aluminum, but then you applied the moles of aluminum directly in the ideal gas law. You can't do that. Aluminum's a metal. It's not a gas. You can't put it into the ideal gas law. So what you had to do was you had to take the aluminum, figure out how many moles of hydrogen you made, and plug that moles into the ideal gas law. Then the other thing you had to do, I gave you the pressure of the water vapor pressure. Okay, I gave you that. You were supposed to use the ideal gas law to figure out what the pressure of the hydrogen was. Then what you have to do, the total pressure is the pressure of the hydrogen and the water. You add the 2 together. That was the other major mistake you guys did on this, was you took the pressure of the hydrogen or of the aluminum, if you use that number, and you subtracted the vapor pressure of water. You got to add it to there. So those are the 2 extra credit questions, because basically, guys, those are the 2 areas that I thought that you had the most problems on. Worth 13 total percent or a little over 10%. Any questions about the extra credit or the test itself, guys? No problem going over the test. I'm hearing crickets, guys. Anything from anybody on there? Welcome back, Aubrey.
Hello.
Okay. By the way, ladies and gentlemen, I'm sorry if this embarrasses you, Aubrey. Aubrey gives excellent advice on the discussion forums, guys. If she gives you something, it's probably dead on. Sorry if I embarrassed you, Aubrey, but it had to be said. Nobody has
Ricky.
any questions about the test? Nothing? Somebody started to say something and I interrupted them. I'm sorry. Other thing, ladies and gentlemen, I did give you a question without a correct answer on the quiz today. Everybody got credit for question 2. Anything else, guys? Before we get started. All right, I have to preface this, ladies and gentlemen, I have to preface this with 2 comments. One of which is thermodynamics is the reason I am not a physical chemist today. By a physical chemist, that is a specific branch of chemistry that involves thermodynamics, thermochemistry, kinetics, and other sundry things such as quantum mechanics. Basically, the math got too much for me in the end. The other major comment I had, by far, this was ruled the hardest chapter of the course in the summer and last spring, by far. So I'm glad you're all here tonight. Okay, with no further ado, shall we get started? Unless you have something else. Can you all see the PowerPoint?
Yes.
Okay, so what we're going to do, we're going to start off talking about energy. By that, I mean potential energy, kinetic energy, and chemical. We'll briefly go through the units. Then we're going to talk about the first law of thermodynamics. We are only getting into the first law in this semester. Next semester in Chem 2, you will get into the second and third law of thermodynamics. We're going to deal with enthalpy of reactions. We're going to deal with calorimetry. I'm going to talk about state functions and Hess's law. Thank you. So bottom line, energy is the ability to do work or transfer heat. Basically, work is nothing more than taking an object of a certain mass and moving it a certain amount of distance. And heat is just the energy that is used to rise the temperature of an object. So that's what we're dealing with. We're dealing with energy, work, and heat for right now. Potential. Now, don't you just want to knock that cat off of that ledge? It's just something about the smugness of the cat's image. Sorry, little side comment. But can you see that if we do knock the cat off the sofa, we have turned the cat's potential energy into kinetic energy. It has potential energy because it is in a higher position than it could be. So that is what potential energy is. It's the energy associated with position or composition. On the other hand, kinetic energy is the energy that is concerned with motion. It's the object energy as it is in motion. And we can literally go from one back and forth to the other. If we're riding a bike, we can ride that bike up that hill, and we have turned our kinetic energy, the motion energy, to being on the top of the hill, and we are now having potential energy. Rocking that bike back and forth, we get it over to the edge, and now we have the energy going out. We have kinetic energy again. So if we have oil in a barrel, we have potential energy because that oil can be burned. We have the potential energy of the composition of the oil. On the other hand, we can have potential energy related to something like Niagara River. Where Niagara River is above the falls, it has potential energy. As it goes over the falls, kinetic energy. And then when it gets down below again, it also has a potential energy that is less than it had before. Now, as I said, chemical energy occurs because of chemical bonds. When chemicals are bonded to one another, they have a certain amount of energy. Now, in order to disrupt that bond, if we disrupt that bond by putting energy in, then we have broken the bond. Now, what happens is we have these particles now that are broken. They want to reform into other bonds. So they react again. The forming of bonds creates energy. Breaking of bonds consumes energy. So this energy has a lot to do with how the atoms are arranged and the types of atoms that are arranged. Energy has got to be added to break the bonds. Then energy gets released as bonds are formed. Now, again, kinetic and potential energies are interconvertible. If we take an object and an object, allow it to fall, we have turned its potential energy into kinetic. We can also take kinetic energy and move it into potential by throwing it up on top of my desk right there. That pen now has more potential energy than it did before, but that's because I threw it up there with the kinetic energy. I always like this slide. This is true in effect, by the way, ladies and gentlemen. Okay, now we have to realize that energy is concerned with two different parts. There is work and there is heat. Work is the distance you move an object times its force. Work is measured in joules. So is heat. The unit of energy that is metric in nature is called the joule, and a joule is moving an object of mass m squared times, I'm sorry, let me back off that, sorry. A joule is moving an object that weighs 1 kilometer by 1 meter squared per second squared. So what we're doing is we're taking the mass and multiplying it by the velocity squared. By definition, that's 1 kilogram moving 1 meter per second squared. There's another unit. The other unit is called the calorie. And when they developed the calorie, they decided to use some things that are fairly common. Water's common. They know that they can measure out 1 milliliter of water. So 1 milliliter of water is equal to 1 gram by its density. So in effect, a calorie came to be the amount of energy required to raise 1 gram of water 1 degree centigrade. And the relationship between the two, a joule, 4.814 joules is equal to 1 calorie. Other units, the calories as you look on a cereal box and you see calories listed, those aren't really small c calories. Those are large c calories or a kilocalorie. A food calorie is 1,000 times more than a calorie used to raise 1 gram of water 1 degree centigrade. Similarly, a kilojoule is 1,000 times what a joule is. Are we all good here?
Yeah.
We're good?
Yeah.
Haven't mentioned anything even new or anything remotely new until right now, have I?
This is all new.
Okay, it shouldn't be. I mentioned some of it earlier on. You have had this an intro if you've taken intro here. Doesn't matter.
I've taken it in other classes, just not chem.
It really doesn't matter. We're going to get it here again. We're going to go into a little more in depth. The first law of thermodynamics, the total energy of the universe is constant. So what that means to you is we have to think about things as systems and we have to think about things as surroundings. We have to define what we're talking about. If we're talking about a specific area, that area becomes our system. That is the thing we want to talk about. The surroundings means everything else in the universe except the system. So system is what we're talking about. Surroundings are everything else in the universe. If we're talking about this piston with oxygen and hydrogen molecules, the system includes the chamber that we're talking about and the oxygen and hydrogen molecules inside. The surroundings is everything outside of this piston. Now, the first law of thermodynamics says the energy of the universe is constant. That means you can't destroy or create energy. So what happens is if your system loses energy, okay? If it loses energy, it is losing that energy to the surroundings. If by another set of circumstances, the surroundings react in such a way as to put more energy into your system, then what's happened is our system has gained energy, but the surroundings have lost it. So what you have to understand is there is that ebb and flow. One gains, the other loses. If the system loses energy to the surroundings, its energy is lower, but the surrounding energy is greater. If, on the other hand, the surroundings gives up some of their energy to the system energy goes up, surrounding energy goes down. So the total energy remains constant. Now, if I'm talking about the internal energy, the sum of all the kinetic and potential energies of all components of our system, we're going to call E. And so if I want to talk about the change of energy, then I'm going to be talking about my final energy minus my initial energy. So if my energy, if my delta E is greater than 0, what this is telling me is my final energy is bigger than my initial energy. And if my final energy is bigger than my initial energy, I've had a net gain of energy in my system. That's going to be a positive number. That's going to be endothermic. On the other hand, if my change in energy is less than 0, then my E final is less than my initial energy, and my system energy has lost energy to the surroundings. My sign is negative, and it's going to be exothermic. Now, I also have to talk about thermal energy, and thermal energy is nothing more than talking about the random motion of atoms. If they move really, really fast, you have more thermal energy. If they're moving really, really slow, less thermal energy. Now, let's see who's out there. Jessica, you out there, Jessica?
Yes.
Jessica, you have a iron skillet that's been in the oven at 350 degrees for an hour. Are you going to touch that iron skillet?
No.
Why not?
Sue will burn me.
Yes. What is happening when you touch that iron skillet, believe it or not? The skillet, if the system is the skillet, then that skillet is losing energy. It has a negative sign. It is being exothermic. It's giving its energy to you. And you have this nice welt down the center of your palm, which has evidence of that energy that's been given to you. You have accepted that energy. So you, as part of the surroundings, have increased your energy. You are absorbing that energy. Your process was endothermic. The skillet lost the energy. Its process was exothermic. It lost energy. It has a negative sign. You gained energy. You have a positive sign. Remember, we can't create or destroy energy. So when you exchange things, when energy gets changed, you do it in one of two ways. You either have work done or you change the amount of heat, because energy is equal to the heat plus the work. Heat being Q, work being W. If you are putting heat into the system and you're working on the system, both of those numbers are positive. You have increased your delta E. Your delta E is going to be positive. Again, our delta E is going to be equal to the work and the heat that are enacted upon the system. These are important, guys. If the system does work, the sign is negative. Jackson.
Yeah.
You ever dug a hole in your life?
Yes.
Did you have more energy before or after you dug the hole?
Before.
Because you did work. So you as a system have less energy because you did work. So if you're doing work, that means that the system sign is negative. The sign of the work is negative. On the other hand, Jackson, have you ever had a massage?
Yes.
You do not need to tell me the circumstances. So if you've had a massage, work is being done on you. You feel invigorated after a massage. So if work is done on you, then you have more energy than you did before. The sign of the work is going to be positive because you're inputting joules into you. By the same token, if we're thinking about heat, even if I'm looking at something as silly as putting a spoon in a flame, what is happening is heat gets transferred. If my system is the flame, when I put that spatula in there, the spatula is taking heat away from the flame. So heat is going from the flame to the spatula. That is going to be negative or exothermic. On the other hand, if I have a cooler object and I'm making it, if I have a cooler object, what is happening is that cooler object is accepting heat, so it now has more energy than it did originally. So that process is endothermic. If the system gains heat, the sign of that heat is going to be positive. In other words, if we add heat to something, that something has a positive Q. If we take heat away from that, it's going to be negative. Important slide. So if heat goes out of the system, heat going out of the system, Q is going to be negative. If my system does work, the sign of that is going to be negative. On the other hand, if I add heat to my system, my Q is going to be positive. Or if I do work to my system, my W is going to be positive. Doing work on the system, adding heat to the system, positive. The system doing work or taking heat away from something, both of those are negative. So if I'm going to calculate the overall change in internal energy for a system that absorbs 326 joules of heat and does 200 joules of work on its surrounding, it's absorbing the heat. It absorbs heat. So my Q is going to have a positive sign associated with it. On the other hand, it's doing work. So my work is going to have a negative sign associated with it. So if I'm doing this problem, my delta E is going to be equal to my Q plus my W. My Q is a positive 326. My W is a negative 200. I add those two together, my delta E is 126. Does that seem to make sense to you guys?
Yep.
Are we okay with that? Pretty simple? We okay? Do I hear an amen?
Yes.
That's not an amen. You disappoint me greatly. Are we okay with this? Seriously, guys?
Yeah, it just takes a little bit of thinking.
Just keeping this thinking and keeping it straight. Was that Jessica?
Rebecca.
Rebecca, sorry. Good for you, Rebecca. Let's look at this second one. My system released 2.73 kilojoules of heat, and it did 7.34 kilojoules of work. Now, if it released 2.73, it released 2.73. Is my Q going to be positive or negative, Rebecca?
Negative.
Okay. Second half, it did 7.34 kilojoules of work. If the system does work, is that sign positive or negative?
Negative.
So I have a negative 2.73 minus 7.34. My total change in energy is 10.07 negative 10.07 kilojoules. Let's see, David, you out there, David?
Yeah, I'm here.
Good. We're going to do this third problem.
Okay.
The internal energy changed by a negative 2.45 kilojoules. And the system released 358 kilojoules of heat. Set the problem up for me.
Well, looking at it, I know that it lost 358 kilojoules of energy because it released it out. The thing that's kind of gawking me is that it changes by the negative 2.45.
So you have negative 2.45 is equal
Originally.
to,
Okay.
that's the delta heat because the internal energy changes. That's what delta E is, David. Okay?
Okay.
So you have negative 2.45 is equal to
Is equal to X minus 358.
X minus 358. So you add 358 to both sides, and you end up with the work that was done on the system, or the work that the system did, being 356 kilojoules, if we want to deal with sig figs. Are we okay? Do you think you can do simple problems like this?
Yeah.
Yep.
We good? We good with that?
Mhm.
Okay, fantastic. Fantastic. And I'm even ahead of schedule. Okay. This is just those problems worked out. All right, now we have to get into a little derivation. All right. And in order to do this, we have to make a couple assumptions. When you're doing a process in the open air, generally speaking, the only work that's done is changing the volume of the gas pushing on the surroundings or being pushed on by the surroundings. So if we want to think of this like a cylinder, basically what we're dealing with is the change in the volume here. Since work is equal to force times distance, and the force is equal to pressure times the area, then we got the P external, the pressure, times the area times the height. Area times height is volume. And literally the area isn't changing. The only thing in that cylinder that's changing is the height. So we literally have our work is equal to our external pressure times the change in volume. Are we good with this one? All right. The only thing we got to account for then is the sign. And we said if the work is done on the if the work is done by the surroundings, that is negative. This is a wrong slide. Ah, crap. I need to change that real quick. Remember, we said work done by the surroundings is negative. Okay, and I guess you guys are kind of lost right now. You don't see this, right? I'll get it back there, I promise. Okay. So if we know that work is equal to P delta V, the only thing we can account for is the fact that it's a sign. When we do work, my delta H increases. So therefore, the signs are going to be opposite. Doing work, delta H is increasing. Therefore, signs are going to be opposite. And I'll account for that in a second. So if I get my work is equal to P delta V. If I do something at constant pressure, and the majority, think about this. How many times do we pump air into a chemical laboratory so that we can do a chemical reaction? All chemical reactions are done at constant pressure because they're done out in the open air. So if it's all done under constant pressure, we can account for something called enthalpy. And we can measure something called the enthalpy of our system. And enthalpy is nothing more than the internal energy plus the product of the work. When the system changes at constant pressure, then the change in my enthalpy, delta H, is equal to the change in the energy plus PV. But remember, pressure is not changing. So in actuality, this delta H becomes delta E plus pressure times delta V. Remember, delta E is Q plus W. And we just said W is equal to minus P delta V. So if I have delta H is equal to delta E plus P delta V, then we have the delta E Q plus W, substitute this in there, and we have the P delta V equal to negative W, the W's cancel. So the only thing I have to worry about under constant pressure is the heat of my reactions. So under constant pressure, if I measure the heats of my reaction, I can determine the thing called enthalpy. That's what this whole thing, this last derivation was all about. If the reaction is under constant pressure, then the enthalpy, the delta H, is equal to the heat that we've either gained or lost. Does that make sense, guys?
Just as an example, so the questions that we just went over, that would mean the answers that we got would be the enthalpy.
No. The reason for that is those questions I had before did not assume constant pressure.
Okay.
It's only when we have constant pressure that we can say that the enthalpy is related only to the Q.
Because it takes that out of the equation.
Correct.
Okay.
Correct. It takes the work entirely out of the equation. Are we good with that then, guys? So basically, as I've just said, the enthalpy, the change in enthalpy is just equal to the heat gained or lost. And we're going to be doing that. You've done these problems in intro. They were called the calorimetry problems. Okay, now, if we put heat into our system, that heat we're putting in there, we're adding heat to it, our enthalpy is positive. It's endothermic. If we take heat out of the system, we have removed heat from our system. Therefore, my delta H is negative, and that is an exothermic reaction. Similarly speaking, the change in enthalpy is going to be equal to the change of the product's enthalpies minus the enthalpies of the reactants. So literally speaking, if I have an exothermic reaction, that means my products are at one energy level, my reactants are at another one. And if my products are at a lower energy level than my reactants, then products minus reactants, I'm going to have a negative number. It's going to be exothermic. On the other hand, if my products have a higher energy than my reactants do, then my products minus my reactants is going to be a positive number. That is going to be endothermic. And what we're talking about is basically the heat of our reaction. It's called the enthalpy of reaction. Think of it like that's how much heat is either absorbed or taken away from the system, and our system is the reaction. Now, do gases have more energy than solids?
Yes.
Yes.
Okay, so wouldn't it be important to know the enthalpy of the things that we're dealing with to know what state they're in?
Yes.
So when we are dealing with chemical equations, we have to designate the states of them. if we don't designate the states of them, then what happens is we don't know where we're starting. So we need to know what state that particular compound is in. Now, when we deal with the heat of reaction for the entire reaction, it has to follow stoichiometric rules. That means if I take methane and add oxygen to it and make carbon dioxide in water, and I measure this out at 890.4 kilojoules per mole, what this 890.4 kilojoules per mole means is that in order for my reaction to go, don't I have to have 2 moles of oxygen? Guys? And don't I have to create 2 moles of water? Guys? Don't I have to
Yeah.
have that?
Yep.
So what happens if I have only 1 mole of oxygen? How much heat have I created?
Half.
Half of that. If I need 2 moles and I only have one, that means I can only create half as much energy. So if I have 1 mole of methane, that means I'm going to make 890.4 kilojoules of energy. Or if I have 2 moles of oxygen, if I have only 1 mole of oxygen, then I have to divide that by 2 because of the fact I don't have enough oxygen. Does that make sense to you? This is stoichiometric rules. If I need 2 moles, then I have to have 2 moles, or else I'm not going to make this same amount. This is kind of like saying 2 moles of oxygen makes 1 delta H. Okay, does that kind of make sense a little bit?
Yeah.
So if I want to convert my O to my delta H, I have to divide it by the coefficient. On the other hand, if I double everything, say I have 2 moles of CH4, 4 moles of O2, 2 CO2s and 4 H2Os, what I have in effect done is I've doubled all my ingredients. I doubled the heat produced. Another important rule. If I reverse my reaction, then the sign of my enthalpy is going to be reversed. So what I mean by that is, if I take CO2 and I put in 2 moles of H2O, and I want to make out of that methane and 2 moles of oxygen, that reaction can be done. But in order to do that reaction, I have to put 890.4 kilojoules into that system to make that reaction go. Whereas if I take methane and oxygen, put them together, I'm going to release that energy. So if we reverse the reactions, the sign of the enthalpy also gets reversed. Sorry about that. Okay, typical problem. If I'm going to make sugar, I can make sugar done in plants all the time. I can make glucose by putting 2,803 kilojoules per mole into a 6 mole water plus 6 carbon dioxides, making 1 mole of glucose. I can make, if I have 6 moles of water and 6 moles of carbon dioxide, I will make 2,803 kilojoules per mole. How much energy would be required to make 1 pound? What's the first step of my of this strategy going to be? What is the first thing I'm going to have to do?
Find the molar masses of the components within your equation.
And then once I have the molar masses,
Compare that to a pound.
let's see, 72 and 12 is 84, and 6 times 16 is 96. Yeah, that's right, 180. The molar mass of glucose is 180. So what am I going to have to do?
Divide 454 by 180.
Okay, I'm going to do that. That gives me 2.54 moles.
And then
Since
we see-
making 1 mole required 2,803 kilojoules per that mole, I just multiply the 2. And in order to make 1 pound of sugar, I'm going to need to put in 7,060 kilojoules. The combustion of methane releases 1,452.8 kilojoules per mole. How many grams of methanol are consumed if 562 kilojoules are produced? Somebody give me a suggestion. I want grams.
Find the molar mass of the combusted reactant.
Okay, so that's going to be 12 plus 3, 15, plus another 16, 31, plus another H, 32. Methane weighs 32 grams per mole.
Okay. That much is produced. You need to divide the 1452 by the 562 to see the percent difference.
Divide the what by the what?
The 1452 by the 562.
If I divide the 1452 by the 562, I get kilojoules squared over moles.
Oh yeah. Okay, wait.
Reverse it. This David?
Yeah.
Reverse it, David.
Oh, okay. Right, because if you do it the other way around, it cancels it out.
If you take the 562 kilojoules and divide it by the 1452.8 kilojoules per mole, that will give you moles, won't it?
Mm-hmm.
But you also have to realize, in order for it to give me 1452, I have to have 2 moles of that. So I have the moles. I did it a little bit differently. What I did, okay, I'm sorry, let me go over this again. This is how much I had, correct, guys? That's how many
Yes.
kilojoules were produced.
Mm-hmm.
And the equivalence is I need 2 moles of methane to make this much energy. Does that make
Right.
sense to you guys?
Yes.
So if I do this out, that means I have 0.774 moles. I simply multiply that by the molecular weight. I need 24.8 grams of methanol to produce 562 kilojoules of energy. Determine the amount of heat in kilojoules given off when 1.26 times 10 to the 4th grams of nitrogen dioxide are produced. The delta H is negative 114.6. Somebody other than David, please volunteer. What are you going to have to do first?
Would you put the moles of NaO2 over the grams of NaO2?
Yep. So you get
So
1
th-
mole for 46. 30, 2 oxygens are 32, and add another 14, that's 46. So in effect, what you are doing is you are turning the grams into moles first. Now, once you have the moles, if I want to find kilojoules, what am I going to do?
multiply it by the kilojoules that it per moles that it gives you in the equation.
Almost. How many moles of NO2 are produced?
Oh, so there's 2, so you'd have to count for that. So you'd have to put that in your moles on the bottom.
So, as you said, I'm going to take my grams and I'm going to multiply that by 1 mole over the grams to get my moles. Then I know that I generate that much heat if I have 2 moles of NO2. So I'm going to multiply this by this, and this means I will have generated 1.57 times e to the 4th kilojoules. How are you guys? Are these making sense to you?
Yeah.
The only tricky
bad.
thing behind this is you have to realize that when you're creating an amount of energy, you also have to account for how many moles made that amount of energy. And you do that by looking at the balanced equation. I'm sorry to keep on going over these guys, but I think really do think that it's beneficial to you. How many kilograms of copper are produced? If you have 1.47 times 10 to the 4th kilojoules of heat that's required in the decomposition of copper oxide. Copper oxide requires 333.8 kilojoules per mole. Let's see, Rebecca.
Yes.
Okay, how are we going to solve this?
We're on the one with copper, right?
What's that?
We're on the one with copper, right?
Yes, we are on the one with copper.
Okay, sorry, your screen's not changing for me. I have to flip through it by myself.
I'm
So-
so sorry.
It's fine. So we change everything to moles first.
Okay, how are you going to do that? Tell me what numbers and what numbers.
So you take the copper oxide and you get the molar mass of that, right?
I'm not saying anything. That's never a good sign, Rebecca.
I'm not sure.
What numbers do you have, Rebecca?
The
Look at the screen and tell me what numbers you do have.
1.47 times 10 to the 4th
Kilojoules.
kilojoules.
What else do you have?
The 333.8 kilojoules per mole.
So is there some way you think you can get moles out of that?
You multiply them or do you divide them?
What's going to give me moles? Dividing or multiplying?
Multiplying.
If I do that, then I get kilojoules squared over moles.
Oh, then dividing?
Dividing what by what?
The 33.8 by the 1.47?
If I do that, then I
Or is it
get.
the other way around? It's the 1.47 by the 333.
I knew you'd get to it eventually. So, but am I dealing with just 1 mole? Look at the stoichiometry.
No, you need
How many moles of copper?
4 to be produced.
So what I'm going to do is I am going to take my 1.47 times 10 to the 4th kilojoules. And as you said, eventually, but as you said, you're going to divide that by 333.8 kilojoules per mole. But that's 333.8 kilojoules per 4 moles of copper. You see that, Rebecca?
Yeah.
So when I do that, I end up with moles of copper. Then once I have the moles of copper, all I have to do is multiply it by the atomic weight. Okay?
Mhm.
All right. I didn't think I was going to get this far. I didn't get nearly this far with the morning class. So we got 10 more minutes, guys. We can introduce the subject of calorimetry. All right. We can't just look at a methane and say, okay, that has so many kilojoules per mole. We can't just look at an oxygen or a CO2 and say that has that many kilojoules per mole. We can't do that. So we have to use something that we can measure. So what we're going to do is we're going to put this reaction in some sort of a vessel that has water in it. We can't stick a thermometer in methane and reliably get the temperature of that methane, but we can stick it into water and get the temperature of that water. And if we get the temperature of the water, we do the reaction. That reaction is either going to be exothermic. In that case, what happens is the water's temperature is going to go up, or if the reaction is endothermic, then the water temperature is going to go down. Does that make sense? Because if it's exothermic, my reaction is now expending heat into the water. That reaction is giving up heat. That heat is being absorbed by the water, and we can determine that heat by measuring the temperature beforehand and after the reaction occurs. If, on the other hand, my reaction is endothermic, it being endothermic, it's got to pull energy from somewhere to make that reaction go. What it does is it pulls energy from the water to make that reaction go. As that energy is being taken off from the water, the temperature of the water will then go down. So we're employing calorimetry by using water as something we can measure and applying it to something we can't measure. So basically what we're going to do, we can do it in a styrofoam cup. 2 styrofoam cups works pretty good. And all we can do is we can measure the mass of the water, measure the temperature before the reaction occurs and after. And we can know that there is a constant that is involved. Let me see who's out there. Blake. Blake.
I'm here. I'm sorry.
No problem. Blake, my iron skillet that's in my 350-degree oven. Would you dare reach in there with your hands and pull that out?
No.
All right. Same circumstance. You have aluminum foil that you're heating a hot dog in the oven.
Yeah, no.
Can you grab that foil out of the oven?
I mean, if you're quick, maybe,
All right.
but it's still gonna hurt.
All right. Let me put it to you this way. You take that iron skillet and you put it on the top of the stove. Okay. You wait a minute. Are you going to touch that iron skillet?
It'll still be hot.
All
So
right.
no.
It'll be more than hot.
Yeah.
Trust me. I have the scars to prove it.
Nice.
Okay. But if you take aluminum foil out, put it on the top of the stove. After a couple minutes, can you crumple it up and throw it in the trash?
Yeah, absolutely.
So the type of substance has something to do with the amount of heat that will be absorbed or dissipated. Is that not true, Blake?
I would agree. Yeah.
All right. Now, if you're going to heat up pasta for my extended family, which is 12 people, I'm going to use my 20-gallon pot of water. All right.
Okay.
As opposed to you're doing it for yourself, that you're probably going to end up using a 2 quarts of water to do your pasta in.
Mhm.
Which one is going to take longer to bring to a boil?
I would say the bigger pot.
Absolutely. The one that has more mass is going to take. So not only does the type of substance have something to do with how much heat is absorbed, but also the amount of the substance. Third thing, Blake, and I'll let you go, I promise, for the rest of the evening. Okay, you're heating a bathtub up to boiling, okay? Or you're heating that same volume of water till it's just nice and toasty, where you can get your little tush in there and have a nice relaxing bath. Which one's going to take more heat?
It'll take more
Basically-
heat to get it boiling.
All right, so we have three things we need to deal with when we're dealing with calorimetry. Our heat is going to be equal to the mass of the substance we're dealing with. It's going to deal with the type of the substance, and that occurs in the form of a constant called the specific heat. I use SH. You may have seen it be used as C. I use SH for a specific reason. So the type also has something to do with it. And then the final thing is the change in temperature. Has something to do with how much heat is going to be required to do what you want it to do. So our Q, our heat, is equal to the mass of the substance times the specific heat times the change in temperature. Water's specific heat is well known and it's quite constant. So we're able to use water as the substance that surrounds our reaction. And then we're going to be able to relate. We're going to be able to tell how much heat the water gained. The heat that the water gained is how much the reaction lost. Is this making kind of sense to you all?
Yeah. So is there any time that like the water molecules will affect the reaction or no? Because it's kind of like a universal solvent.
The amount of water that we're talking about compared to the amount used in a reaction is insignificant.
Mm.
Like, for example, if we're doing a combustion reaction, that methane, remember the methane reaction?
Yeah.
That's back here somewhere. Oops, I'm going the wrong direction. Trying to find, I just don't know what that is right off the top of my head. Okay. All right. We're dealing with waters being produced. Oh, this is methanol. Okay. We're dealing with my methane reaction here. All right. Methane weighs 16 grams, right?
Yes. I'm not sure.
Yeah, 12 for carbon, 4 for hydrogen. Okay. So if I'm going to deal with a mole's worth of methane to make this much heat, I'm dealing with, yes, 16 grams of this. But the amount of water that, okay, if I'm dealing with 16 grams of this means I'm making 32 grams of, or 38 grams, 36 grams of water. Okay. But to get this much heat, to just be able to dissipate this much heat reasonably, I'm going to have to use a whole lot of water. So the amount of water I'm generating is not going to be, is going to be inconsequential to the amount.
Gotcha.
Jasmine, right? Or is
Rebecca.
it Jessica? Rebecca, sorry. I still have a hard time recognizing voices.
It's okay.
So basically what I'm trying to say is the amount of water that's produced is inconsequential to the amount of the reservoir of water that's there.
Mhm. Yeah.
And guys, that's where I think I'm going to end for right now. We are literally nope. This is about where I ended with them. Sorry, we're about 10 slides ahead of them. Okay. We're about 10 slides ahead of them. So no big deal. Anybody have any questions about what we went over today? I really want you to know the change of energy is equal to Q plus W. I need you to know those. I need you to be able to convert. If you have the enthalpy of reaction, I need you to be able to convert that back to how much of the stuff you need to create that much energy, or if you have that much stuff, how much energy you create. This is going to be the third equation we're going to need to know. Do I have any questions about what went on today? Or the test? Remember, as of, I believe in 17 minutes, the extra credit will be open. It's going to be open until 9 o'clock on Thursday. Worth 13 points. Okay? Other thing is that if you didn't see my announcement, second question on today's quiz was a freebie because I didn't put the correct answer in there. Anything else, guys? That's all, folks.
Thanks, Professor.
Take care, guys. Those of you who are in the lab, again, I'm going to have to wait until 7:30. I'm sorry. Maybe
Yeah, no worries.
maybe in 45 minutes you can get something thrown down your throat.
That's the plan.
Glad that's a plan for you.
Thanks for the extra credit homework too. That'll really
Not-
help me. So I appreciate it.
No problem. You guys did a fairly incredible job on the tests. The only reason you're getting this is I had like 4 or 5 people that did really horribly on the test.
Well, I could have been one of them. I put in a lot more work in this go round than the first time, so it kind of paid off, but I could still use the help, so appreciate
Well,
it.
I'm sorry, who's this?
It's Blake.
Blake?
Yeah.
Well, how did you do? I didn't think you did that poorly.
I didn't. No, I was thinking for a B, but I got slightly lower than a B, but I was still overall happy. Did much better than the first go round, so.
Well, I mean, this 13 points is going to push you up.
Yeah, for sure. So I appreciate it, man. Alrighty. Till
All
next
right.
time.
See you later, guys.
See ya.
I had a question, Professor.
I'm here.
I believe you had sent an email back towards the beginning of the semester, but I just wanted to clarify. The homework that is done on the online portion or the actual homework, when will that be inputted into the grade book?
At the very end.
Okay, thank you.
It's gonna, yeah, it'll wait till the very, very end. Yeah, I have some things I have to do, and the things I have to do with the homework, I have to wait until the end of the semester before I fully implement that into the grade book. Okay? All I can
Okay,
tell
thank you.
trust me. Trust me, it's going to be a score that's better than the score you have right now. Okay?
Okay.
Anything else, guys? Remember, if you're in the lab, we're going to go until we're going to wait till 7:30. Take care. I will see you on Thursday then. Take care, Ian.